Come back. So we want to illustrate the mean value theorem with an example. So let's consider fx equals x cubed minus x. Let us have a and b to be 0 and 2 respectively. Since f is a polynomial, yeah, it is continuous. It is also differential because you can take derivative. There are no denominators, no square root. It's really fine. Is differentiable for all x. So it's certainly continuous on closed interval 0 2 and differentiable on open interval 0 2. Therefore, by the mean value theorem, there is a number c in 0 2 such that slope of the tangent at c, right, is equal to the slope of the line segment joining at the endpoints, right, 0 and 2. So f2 minus f0 over 2 minus 0. They have simply cross multiplied and gotten 2 minus 0 here. So this is the result of mean value theorem. So let's figure out what is f2. f2, plugging in 2 here, you get 8 minus 8 minus 2. f2 is 6. What about f0? Plugging in x equals 0, you get 0 minus 0, 0, right? What about the derivative? Well, what is derivative? 3x squared minus 1. 3x squared minus 1. Now notice we want to find the derivative at c. So instead of x, you need to plug in c. So left hand side is 6, right? 6 minus 0. Right hand side is 3c squared minus 1 times 2. 2. Where did this 2 come from? It came from 2 minus 0. All right. Distribute the 2. You get 6c squared minus 2. Fine. 6 equals 6c squared minus 2. Move the 2 over. That gets you 8. So c squared is 8 over 6, which is 4 over 3. Okay, calculate this yourself. You will see c equals plus or minus square root of this quantity. So 2 over root 3. But we are looking at a number which lies between 0 and 2. So the negative option is out. We therefore take only the positive option. So that number gives you slope which is equal to the slope of the line segment joining the endpoints. So here is the picture. Your curve x cube minus x is given by this black curve. 0 and 2 are your endpoints. So the line segment joining those two, yeah, looks like this. Notice there is exactly one point in between which has the same slope, equal slope as this line joining the endpoints from 0 to 2. All right. Next, suppose that f at 0 is negative 3 and f prime x is less equals 5 for all values of x. How large can f2 possibly be? Aha. Now this is a nice kind of problem. What does it say? At 0, I have height negative 3. And after that, for all values outside of 0, all values, the slope of my tangent cannot cross 5. It has to be less than or equal to 5. So how large can my height at 2 be? Well, we are told f is differentiable. Well, that's why we can find the derivative. If somebody is differentiable, then they are automatically continuous everywhere because that's what it's saying, all values of x. In particular, why don't we just go from 0 to 2, closed interval. My function is continuous here and differentiable in the open one. So there must be a number c between 0 and 2 where the derivative satisfies this formula, right? f2 minus f0 equals f prime c. What do we know about f prime c? Well, all derivatives are less equals 5. So f prime c has to be less equals 5 also. So, okay. So f prime c has to be less equals 5 also. Now notice what they have done. They have distributed the 2. Well, they have just 2 minus 0 is simply 2. Okay. Then move the f0 to the other side. They have moved the f0. So that's all. Okay. f0 we were told is negative 3. All right. So you are negative 3 here and 2 f prime c. Now we know that f prime c is less equals 5. So multiplying by 2 gets you 2f prime c is less equals 10. So this entire quantity is less equals negative 3 plus 10, that is 7. In other words, f at 2, the height at 2 has to be less equals 7. The largest possible value for f at 2 is 7. Okay. Next, the mean value theorem can be used to establish some of the basic facts of differential calculus. If the derivative is 0 throughout, then f has to be constant. This is a deep result. You see, if f is not constant, then it will go up or down somewhere. In which case, derivative cannot simply be 0, right? You have to have some positive derivative or negative derivative. So, if the derivative is forever 0, then f has to be constant. Likewise, if two functions have equal derivative, then what do? I bring this to the left hand side. Then f minus g will have 0 derivative. In other words, f minus g is constant. Alright, if f minus g is some constant, then f equals g plus that constant. Alright, so I hope this is clear. F prime equals g prime, so move the g prime to the left, you get f prime minus g prime equals 0. Like that. Something equals 0 means that thing, yeah, something derivative equals 0 means that thing is constant. So f minus g is constant. Okay. Now, care must be taken. Look at this function. Fx equals x over absolute value x. When x is positive, absolute value x is x, right? So you get 1 above. But when x is negative, the denominator is positive, but numerator is negative. So you get a negative 1. But this is not differentiable. Okay? So one has to be very careful. It is f is constant after 0, f is constant before 0, but it is not defined at 0. So we are looking at two separate intervals. All right, so be mindful with theorem 5. It's very important. If your function is continuous on an interval, derivative is 0 on that interval, then f is constant on that interval. Okay, so you need one particular interval where the derivative is 0, then f is constant there. Okay. All right, so next slides on, I will go over problems from web work on this particular topic, section 3.2. Until then.